Hi, this is Alexandros Latas from Imperial College London, and I will present to you FitMe, a deep 3D morphable model capable of generating explicit facial and head avatars that can be photorealistically rendered. FitMe requires only an arbitrary facial image as input. We use a deep model of facial reflectance and a shape model to perform iterative fitting, which is optimized by differentiable rendering. Within a minute, we acquire an avatar compatible with common game engines. To achieve these results, we use a multimodal GAN and accurate diffuse and specular rendering in a two-step optimization. FitMe also works with multiple images. We concurrently generate high-resolution reflectance maps so that the optimization can be guided by fast and accurate rendering, achieving unprecedented likeness for relatable avatars. Scanning facial appearance started with a light stage, a room-size LED dome, which requires expert operation and long capture sequences. Although recent works greatly simplify the process, they still require expensive equipment and constrained capturing. 3D morphable models have been used to acquire facial assets from in-the-wild images, with the albedo morphable model first modeling facial diffuse and specular albedo, but being limited by its linear model. Previous multimodal deep models also failed to produce accurate fittings. Lu et al. Achieved albedo acquisition using a style-based generator, while Avatarme acquired high-resolution facial reflectance from arbitrary images, but was limited by its use of multiple models. Combining the best of both worlds, FitMe uses a single powerful generator and differentiable rendering to acquire fully relatable facial shape and reflectance from arbitrary facial images. We introduce BRDF GAN, a multimodal, style-based generative network which concurrently generates facial albedo, specular albedo, and surface normals. Based on StyleGAN, BRDF GAN consists of a mapping network and a multimodal branch synthesis network. During training, we also introduced a branch discriminator. We observed significantly different statistics between both albedo and normals. By branching out most of the discriminator, we can model the distributions much more accurately and achieve lower FID. For the shape, we retain the usual PCA model to avoid redundant parameters and improve generalization. The reflectance maps generated by our model are rasterized on each iteration and used for accurate diffuse and specular shading. We use the Blinn-Phong model for the diffuse and specular components based on a set of point light sources. The specular component is crucial, not only for improving the shading quality, but also to provide feedback for the specular albedo and normals. Moreover, we use the smoother shape normals as diffuse normals to approximate subsurface scattering, which we also approximate by performing texture space blurring. By adding both components, we acquire the final rendering. We perform the optimization of the model in two steps, rendering-based GAN inversion and tuning. During the inversion step, we optimize the model's latent parameters together with the shape model's identity and expression parameters, as well as the camera and illumination. In each step, we render the reconstruction and acquire feedback using photometric, identity, perceptual, and regularization losses. During the tuning step, we freeze the latent parameters and perform a version of pivotal tuning on the generator, using a set of perceptual, photometric, and albedo regularization losses. Since this is a multimodal GAN, we only optimize the middle layers of the network. We find that the first layers control the overall color and the albedo may absorb illumination, while the last layers may reproduce noise from the target image. To train the model, we obtain a dataset of facial textures and use a fine-tuned Avatarme model to obtain the reflectance maps for each subject. Moreover, we introduce a masked histogram matching method to augment the skin tone variation in the acquired albedos, using a few target albedos matching the MST scale. Our histogram matching method for skin tone augmentation compares similarly with biophysical models while requiring a fraction of computing time and no multispectral data, while it is also outperforming inverse rendering methods. Using a single arbitrary facial image, FitMe recovers facial shape and reflectance with high identity similarity, beating the current state of the art, even Avatarme, which was used for the training data. as we optimize directly on the image space using accurate differentiable rendering. Also, our method outperforms prior art on quantitative identity preservation. Here, we show a comparison with a captured and manually processed subject, Digital Emily. FitMe acquires scan-like reflectance materials when using either one or three inputs, while the actual scan requires dozens. We also show a comparison with a challenging illumination input. As an application, FitMe makes it easy to acquire a relatable facial avatar using only a couple of unconstrained selfie images. By recovering high-quality albedo and normals, these avatars can be related to any environment. Moreover, using our powerful generator, high-quality head avatars can be acquired from even low-resolution internet-sourced images. Finally, the recovered assets include a typical mesh and corresponding UV maps of facial reflectance. Therefore, they can be used as scenes for rendering in common gaming and rendering engines. Regarding challenging cases, FitMe produces pleasing and relatable avatars even when presented with headbands, glasses, or even makeup. Moreover, we show smooth interpolations in the latent space between different results, showing that our model learns a smooth and continuous latent space. Finally, by performing PCA on the model's latent space, we can manipulate the principal components after performing reconstruction and manipulate certain features such as skin tone or facial hair. This wraps up the overview of FitMe, a deep 3D morphable model of facial reflectance that produces relatable avatars from unconstrained facial images. Please follow the link below for the paper and project page. Thank you for your attention.